Voila. Minoan mudbricks are sun-dried instead of being fired in a kiln. This makes it possible to speed up the production process, but it has a major hindrance, namely that unless they are located near a constant source of heat or taken in a heavy destruction by fire, the mudbricks melt. For this reason, this building material is often missing from standing architectural remains and hence from excavation reports and synthetic publications on Minoan architecture. Another reason why mudbricks are often neglected from Minoan architectural studies is that the best preserved site of the Bronze Age Aegean, Akrotiri on the island of Tira, shows only rare instances of mudbrick use. Buildings in Akrotiri are preserved up to several floors high, but they are chiefly made of stones, and mudbricks only appear there in the form of upright standing elements forming beams or parapet. So Minoan archaeologists, who often refer to Akrotiri for in situ architectural comparisons, find little evidence pertaining to mudbrick on this site. Despite difficult conditions for its preservation, mudbrick is often recovered in fragments in archaeological deposits. The problem, and it is based on our site experience, is that unless they are of large dimensions or show several plane surfaces, these fragments are generally only briefly mentioned in excavation notes and left uncollected, and thus remain unstudied and unpublished. This is due on many sites to the lack of storage space for archaeological finds, but it is a pity because in the field, the archaeologists are not given the time and conditions for properly identifying earthen building materials, and very often what is quickly identified as mudbrick can be as varied as sailing fragments, tiles, mud coating fragments, or parts of any type of earthen installation, including door jambs and window sills. All these earthen elements share a similar composition with mudbricks, but they are in fact entirely different architectural features. Besides difficult conditions for their preservation, another reason why mudbricks are often absent from published reports and synthesis is that this building material is seen as structurally weak, with limited bearing capacity and low resistance to atmospheric conditions. But laboratory tests on the tension and compressive strength of sun-dried mudbricks have demonstrated their load-bearing capacity. And this load-bearing capacity can even be improved using a wooden framework set within the wall or by the incorporation within the mudbricks of fibrous material. Also, the often criticized limited resistance of sun-dried mudbricks to moisture can easily be dealt with. A stone socle can prevent erosion by capillarity and protect the mudbricks from potential floods. And wall erosion can be prevented by mud and/or lime plaster and by the regular maintenance of this coating. In fact, contrary to the general opinion, mudbricks show marked advantages in comparison with other materials. They offer better resistance to lateral shocks. Their thermic performance allows the slow transmission of heat or cold. They better regulate humidity, and they can resist fire destructions, which might freeze the walls instead of provoking their collapse. Archaeologists have grown increasingly aware of mudbrick potential and importance in the Aegean Bronze Age, and one must underline the growing attention paid towards mudbricks in a number of preliminary and final excavation reports on Minoan sites and in synthetic studies. The elaboration of new protocols for the systematic recording of earthen elements during excavations or study. And I give you here the example of Sandra Prévost-Dermacar's paper in the BCH, where she proposes a standard recording system based on her own experience in Dikili-Tash. And also, more generally, there is a growing interest for building materials other than stone, and the recognition that mudbricks, together with other materials such as wood, must once have formed a substantial part of Minoan buildings. The objective of tonight's seminar is to present the results of an architectural and geoarchaeological study of mudbrick remains within the palace at Malia. In the first part, I will present in details macroscopic observations of the individual mudbricks and their bricklaying techniques. In the second part, Marta will present the results of a series of geoarchaeological analyses which she made on a selection of mudbrick samples. Our ultimate aim, which will be addressed in the conclusion, is to combine these macro and microscopic approaches in order to gain insights on the organization of the Malia Palace building project and on the craftspeople and laborers who participated to its construction, and thus to demonstrate the importance of studying this often neglected building material. Several Minoan sites have produced more or less substantial mud brick wall remains, standing or in fragments, and we will focus today on one specific site and building in Malia, a major site on the north coast of the island of Crete, first excavated by Joseph Hatzidakis in 1915, and then explored by the French school at Athens since 1921. Malia constitutes an interesting case study because a series of violent destructions by fire in the late 3rd millennium and throughout the 2nd millennium BC have burnt and preserved many mud brick walls. The abundance of preserved mud brick remains has often been related to the geological setting of Malia. As we will see in more details later in this presentation, the Minoan site is located on a hard gray-blue limestone plateau called sideropetra because of its high iron content, and this limestone decomposes into terra rossa, a red soil which forms the main ingredient of the mud brick fabric. It is worth reminding the care taken by Hatzidakis and the French school in protecting the mud brick remains in Malia. To illustrate this, one must remind the wall built by Hatzidakis in 15 or 1919 in order to support an upper elevation of mud brick in the palace, but also the construction in 1931 of a modern stone shed on top of the eastern magazines of the palace in order to protect the mud brick walls and for storing the finds discovered in different parts of the building. And also the temporary roofs built on top of the walls in different parts of the site during or shortly after excavations. You have here the example of Quartier Mu, but it was also the case in the hypostyle crypt and the palace. These protections were removed for the construction in 1992 of the beautiful roofing systems created by architect Martin Schmidt in the palace, hypostyle crypt, Quartier Mu and Sanctuaire aux Cornes, restored in 2013, and which have allowed the preservation of substantial mud brick walls. The palace at Malia has a long and complex history, which will be presented here in a very synthetic manner following the main periods of the building. Remains including mud brick walls were already built at the location of the palace in the second half of the 3rd millennium BC during the pre-palatial period, marked here in blue. But if we agree that a Minoan palace, for being called so, has to have several wings bordering the central or main court, available evidence suggests that the palace at Malia was first built around 1900 BC. This first or proto-palatial palace, in orange, is used until a major destruction around 1700 BC, after which it is rebuilt to form the second or neo-palatial palace in green, which is used until around 1450 BC. The 3rd millennium pre-palatial remains of the so-called Kazmat, situated in the west wing of the palace and dated by a foundation deposit to the early Minoan 2B phase between 2450 and 2200 BC. It consists in 4 mud brick walls set on a low stone socle, which were fired in the destruction and were later incorporated in the Middle and Late Bronze Age palace. The eastern wall is still preserved on a height of 1 meter and 93 centimeters. This is the one you can see on the orthophotograph. The mud brick walls of the eastern magazines belong to the proto-palatial palace. These narrow parallel rooms were provided in the proto-palatial period with low sandstone platforms that supported large storage vases. The walls delimiting such rooms were made of mud bricks, and they were reused with slight modifications in the later palace of the neo-palatial period. But most standing mud brick remains are dated to the neo-palatial period. Olivier Pelon had suggested the reconstruction of the edifice around 1600 BC, but it is possible that the revision of the stratigraphic and ceramic sequence will bring this date upwards in the 17th century. The NonPalatal Sample is especially interesting for the variety of mud brick walls. Some are part of coherent, spatial, and possibly functional units, while others are simple partition walls, and their masonries and mud bricks composition vary strongly. The study of the Malia mud brick walls has highlighted a series of features worth recording for understanding and comparing them. These concern the stone foundation and/or socle, the type of bricklaying within the mudbrick course, the alternance of mudbrick courses with leveling layers of plastic earthen material, information pertaining to the composition of the mudbrick, color, inclusions such as mineral, vegetal, and anthropic elements, and information pertaining to coating of varying type and composition. Mudbrick courses are generally laid on top of a stone socle made of rubble and/or boulders of the local hard gray-bluish limestone, or more rarely conglomerate, a stone which is also procured locally. Both exterior and interior walls show substantial stone sockles ranging from 20 to 58 centimeters in height. As we underlined in the introduction, the purpose of the stone socle is to avoid the decomposition of the sun-dried mudbricks by preventing moisture to reach up by capillarity. Only in rare instances is the stone socle absent, in which case the mudbricks are set directly on a stone foundation course. The stone socle is generally closely associated with a 4 to 12 centimeter thick leveling layer of plastic earthen building material, the PEM, which is made of sediments with added vegetal temper, which creates a plastic mixture which can be easily shaped. The top of this PEM layer is carefully flattened in order to support the upper courses of mudbricks, and in several walls, stones of small dimensions, 5 to 10 centimeters, are stuck into the PEM layer in order to function as stone wedges and to increase the stability of the socle. Oops. In all the earthen walls of the palace, the mudbricks are laid in superimposed courses separated horizontally by a 1 to 3 centimeter thick mud mortar joint and vertically by thinner joints of 1 to 1.5 centimeters. In several instances where the walls are preserved on a sufficient height, layers of PEM measuring 6 to 16 centimeters in thickness are set as intermediary layers that often incorporate stone wedges of small dimensions, although there are also cases where larger rubble stones are used. The function of such intermediary layers of PEM and stones is identical to the PEM layer topping the stone socle, which is to level the masonry before additional mudbrick courses are set. In most cases, the mudbricks are laid in header bond, which means with one of their shortest sides on the wall face. But running bond, that is with the mudbrick set in stretchers or with one of the longest sides on the wall face, is common in partition walls. It also regularly happened that the builders set bricks in a different position from the most common bricklaying to better fit the dimensions of the wall, so that it is not uncommon to find mudbrick specimens set upright in the wall. There is also one example of English bond with successive courses of headers and stretchers in the north wall of the pre-palatial Kazmat. And as you can see on the illustration, the gap between the courses is filled with plastic earthen material with small stones. In the pre-palatial walls of the eastern magazines, the bricks are laid in header bond, but the specimens are offset horizontally within the same course. The gaps thus created are filled with small stones and mudbrick fragments set in PEM. This bricklaying made it possible to create a wall wider than the brick's length, and at the same time, the plastic nature of the PEM provided a cohesive link between the components within each course. The incorporation of wood as a structural element in Minoan walls has been stressed in several studies, and I'm thinking especially about the work of Petrographic. But there is surprisingly little indication for the use of wood in the mudbrick walls of the palace at Malia. Several impressions of vertical wooden supports are found, but the examples are quite rare when compared to the large number of preserved mudbrick walls in the building. The scarcity of indication of the mudbrick wood association in the palace may be due to the fact that mudbrick walls in the edifice are rarely preserved above 80 centimeters. Observation of the mudbricks used in the walls of the palace at Malia has shown that their macroscopic fabric composition, which means that is visible to the naked eye, range from fine to coarse. Mudbricks with a homogeneous fine macro fabric are usually reddish in color and are produced with a screened sediment with a maximum gravel size of 1.5 centimeters. These sediments are mixed with large quantities of marine seagrasses, and contain minimal other inclusions. Mudbricks with a heterogeneous coarse macrofabric are more varied in color and are manufactured with sediments which have not been screened so that they present numerous large inclusions, such as large gravels, obsidian, bones, shells, plaster, or ceramic fragments. It is also striking that the macrofabric of these coarse mudbricks present fewer seagrasses than the fine ones. We noticed that the mudbricks with a fine macrofabric erode less easily, and in some cases, minute details related to their fabrication are still visible on their surface. You have here the example where fine vertical grooves left by the wooden mold when it was removed from the mudbrick are still visible. So it is noticeable that the macroscopic composition of the mudbricks strongly affected their performance. The finer, the better. The coating of mudbrick walls with mud plaster protected them from erosion, humidity, and parasites. Where it is preserved, the mud plaster is composed of a sediment matrix ranging from red to reddish yellow with large quantities of straw, up to 60%, in stalks 3 to 10 centimeters long. The incorporation of straw in the mud plaster matrix reinforced the structure of the coating. It also reduced the risk of it shrinking and cracking by helping the drainage of excess water outside the mud coating. Only in some rare instances were seagrasses identified in the mud plaster, where their presence seems accidental. And this difference in composition between mudbrick and mud plaster is especially useful when earthen building fragments are found in excavations, since the presence of seagrasses or straw may help to distinguish between mudbrick and mud plaster. On some walls, multiple superimposed layers of mud plaster show the gradual refining of the mud plaster composition, with a thick layer, 3 to 10 centimeters, of coarse mud plaster used to even the surface of the wall, on top of which one or several fine layers of mud or lime plasters were applied. Ethnoarchaeological sources indicate that these finer layers had to be maintained regularly to protect the wall efficiently, likely once every 2 or 3 years. So the macroscopic observation of the mudbrick walls in the Malia Palace has shed light on a series of key masonry features, such as sockles, bricklaying, PEM layers, mudbrick macroscopic composition, and coating. It has also highlighted the diversity of the mudbrick walls that formed the building. But before interpreting this diversity in terms of the construction process, we wanted to go further into the study of the mudbricks composition through a series of geoarchaeological analyses, which Marta will now describe to you in detail.
Thank you. Can we go to the next slide? Thanks. So, as Maud was explaining, the macroscopic analysis of palace architecture in Malia encouraged us to conduct a geoarchaeological study to highlight if what we could see macroscopically was also reflected at the microscopic level. Our research idea was and is that the combination of macroscopic and microscopic data allows us to have a more comprehensive understanding of mudbricks as a form of material culture, not just as building materials. Mudbrick, at the end of the day, are a human production. And as such, an interdisciplinary approach makes possible to inform not only on the technological aspects of this production, but also on the social and cultural norms accepted by the group who is manufacturing them. So we come up with 3 research questions that focuses on specifically providing an answer about continuity in raw source material procurement, in manufacturing technique, and in construction technique. What we were hoping to achieve is to determine if there is any change in how raw sources are actually procured for the production of mudbrick, and if there is a change in manufacturing, which type of change is occurring? Is it diachronic or synchronic? So we designed a methodology, next slide, Thank you. We designed a methodology in order to answer these research questions that combine geochemical and petrographic analysis. Specifically, the analysis presented here: X-ray fluorescence, X-ray diffraction, scanning electron microscope, Fourier transform infrared spectroscopy, and thin section petrography. I have previously successfully completed a pilot project for my PhD research. So we were optimistic when we come up with this methodology that this analysis would provide us with the data to answer the research questions that we formulated. Next. Because I was not completely sure on how familiar the audience tonight would be with the chaîne opératoire behind mudbrick manufacturing, and I imagine not everyone is a mudbrick nerd, as I think Maud and I would both define ourselves. I thought it would be nice to give you a bit of background on what is actually happening behind the manufacturing process. I usually use this fresco that is coming from the Reckmeyer tomb. It was a vizier of the 18th dynasty, but it's also a perfect breakdown, sort of a comics breakdown of the full chaîne opératoire of mudbrick manufacturing. So you do have the first phase, that is the collection of the raw materials. You do have the mixing of the raw materials with water and different type of tempers. Then you have the molding of the bricks. The fourth phase is actually the drying, that is dependent on climate condition. So the drying period in Egypt is clearly different from what we do have in Crete, or we would have in Anatolia or other regions. And finally, once the bricks were dried, they were stacked, and they were ready for the last phase, the construction, the building phase. Next, thank you. For our geoarchaeological analysis, we conducted all the set of analyses that are presented on 15 samples that we collected in situ with a scalpel on the standing wall of the palace. The rationale behind our sample strategy was to collect fragments ranging from the pre-palatial, roughly from the early Minoan 2B period up to the Neopalatial period, so from the early to the late occupation of the palace. We also tried to sample bricks that were coming from different wall typologies, so both exterior and interior walls, and from diverse functional areas within the palace. For completeness sake, I have to say that in my full study of Malia, I also sampled other 15 walls from Quartier Mu and 30 from Quartier Delta, because the mudbrick were not sampled from standing wall, like we agree with the FRE and the ministry for the palace and Quartier Mu, but they were coming from excavation. So the sampling strategy was a balancing act between preserving what we have at the moment at the palace and also be able to conduct this type of research. The first analysis then we conducted was portable XRF, which is a point and shoot non-destructive technique. And again, I gave you here a bit of a breakdown on what actually is happening. So when the X-ray hit the sample that is usually performed with a portable XRF gun, it emits an X-ray characteristic wavelength, which is then received by the detector. I indicate, like in the spectra presented in the slide, the elements presented in the sample in that specific point. So in order to be able to standardize our findings, we have taken multiple measures from each sample that they were then averaged and normalized during the statistical analysis. Next. One of the first statistical analysis we performed was the principal component analysis based on the elements that you see on the left. So zinc, iron, manganese, rubidium, titanium, strontium, and zirconium. As you can see, the two main principal components, PC1 and PC2, explain 73.2% of the total variability. And the result shows two overlapping ellipses, which indicates that although our number of samples, it's quite limited, it's just 15 samples, seems to indicate a general pattern of consistency and continuity of raw material sources over time. If we go to the next slide, I just wanted to widen a bit my explanation on this. In this case, you see the principal component analysis that is being performed on all the samples that I collected in Malia. And you can see that the different ellipses indicating the Palace, Quartier Mu and Quartier Delta. The majority of the sample was actually coming from the building Delta B, but we also had sample from Delta Alpha and Delta Beta. Show the same pattern of continuity and consistency of raw sources, indicating that this consistency, the chronic consistency, is not just present in the Palace, but in all of the settlements in Malia. These results were further supported by other statistical analysis, such as the Scattergram, which is mapping iron, rubidium, and strontium through a methodology that has been trailblazed by Morgenstern and Redmond in their analysis of mudbrick architecture in Egypt through portable XRF, and then is now being widely implemented around the world. In this case, strontium is a proxy for carbonate content, whereas rubidium is a proxy for mica and elytic mud, and iron for the non-carbonate silt detritus. As you can see, also in this graph, the cluster, it's quite tight, representing the continuity of raw source material. Now we go back to the samples and specifically the topic of this presentation, what's happening with the mudbrick in the Malian Palace. Our next step was to perform a bivariate analysis by isolating the value of iron, manganese, and strontium. The points are discriminated here on the different dots, the samples are discriminated here on the basis of the location of the sample within the palace. To briefly explain, strontium, as I mentioned before, is associated with carbonated rocks, while iron and manganese refer to the non-carbonate content, such as ferromanganese silicates or elytic mud. Specifically, when we look at the graph on the left, where is presented iron versus manganese, we see an open arrangement of points that indicated mudbricks that share a similarity macroscopically, what Maud was before earlier presenting as heterogeneous or homogeneous. Mudbrick can show chemical dissimilarity. One example, for instance, is Ma2 and Ma15 from Corridor C. But more important, both graphs, both scatter plots, indicate a clear division in two main groups that show the chemical similarity between samples located in nearby walls, such as Ma9 and 10, 13 and 14, 7 and 8. Thus, referring back to the image of the chaîne opératoire that I showed you earlier on, this indicates that these mudbricks were produced within one single manufacturing phase, while their assignments to neighboring areas of the palace suggest a cluster construction development. Our next step then was to perform Xray diffraction. We performed this analysis by crushing the bricks, and it was performed at the Democritus Institute in Athens on 4 samples coming from the palace. And it was performed to identify the type of clay used in the mudbrick production and to determine which other elemental components, such as calcite or dolomites, were present, we could find within the mudbrick samples of the palace. The results indicates that elite muscovite, a non-expansive type of clay, is the main, the main type of clay used in the production of the mudbrick in Malia. Aside from quartz, other relevant component identified in the spectra was the calcite, especially if you look at the spectra of sample number 14. which reflects the incorporation of fragmented lime plaster in the recipe during mudbrick manufacturing. Here it's an example from nearby where we took the sample number 14. And thus indicating the likelihood that building materials, especially old building material, were crushed and remixed during the mudbrick manufacturing. When we compare the geochemical analysis that I briefly presented here to the geological map of the area, it was possible for us to determine that raw source procurement was actually occurring within a 2-kilometer radius from the core of the settlements. In fact, within this 2-kilometer radius, we have easily accessible clay beds, alluvial sediments of similar elemental composition, but even samples that show, such as Ma2, that shows peaks that are quite foreign to the other samples, such as dolomites and iron oxide like magnetite and hematite, can be reconnected to geological sediments that are present within this 2-kilometer radius. In the specifics of sample number 2, the limestone geological deposit, as well the Agia Varvara formation and talus cone are present on the west and the south of the site. Then we perform FTR and SEM, and this was more of try to understand better the taphonomic bias that it's affecting mudbrick manufacturing. As Maud mentioned before, even though mudbricks are mentioned in most of the excavator diaries, we do find little when we are actually conducting the excavation. And this is part for climate condition and taphonomic bias, but it's also because the only materials that are preserved, they are the mudbricks that have undergone a conflagration event. And in this case, this is quite visible in the FTR, where show the absence of structural water and the shift of the main clay peaks that actually occur during a conflagration event. You can also see the initial signs of vitrification in the SEM photo. The final phase of the geoarchaeological analysis was the Petrographic Study. And this indicates the presence of a main fabric, which is characterized by the reddish-brown matrix and a limited number of inclusions. These inclusions are mainly monocrystalline and polycrystalline quartz, feldspar, iron oxide, nodules, and clay pellets. The presence of a human-induced tempering, such as lime fragments, was also documented. And this is quite common for people who are familiar with the mudbrick manufacturing process. This is quite common, as often crushed lime plaster or even crushed pottery, and this is what the grog refers to, are mixed with the vegetal temper to prevent the shrinking of the brick during the drying phase. We put on the left of the slide the only outlier that we have within this fabric. This is MA5, sample number 5, and this is the exception to the main fabric, since it presents a calcarenite fabric with a brownish color and the presence of micritic calcite grains. This is actually an outlier within all the other samples that we do have in the Palace of Malia, but it's not an outlier in the whole settlement. Similar mudbricks are actually, of a similar fabric, are actually found both in Delta and Quartier. The study of the petrographic fabrics, though, highlighted several other interesting aspects of Minoan manufacturing. First, the presence of different vegetal tempers is indicated by a different type of voids and impression left by chaff and seagrasses. Void left by seagrasses are usually wider and longer than the one left by chaff. And you can see that even macroscopically, because usually chaff can be 2-3 centimeters long, whereas the seagrasses are from 10 to 15 centimeters long. Chaff voids are also mainly visible in the pre and the protopalatial samples, whereas seagrasses are visible starting from the protopalatial sample, but there is a huge increment in the neopalatial samples. Second, it was possible to identify microfissures caused by the progressive evapotranspiration of water-lane sediments, as the seagrasses inside the bricks cause long-term water retention. Third, you can see in the dotted line here, we identify some rotating features that could be associated to manufacturing practices such as kneading and pugging. And finally, we could distinguish two microfabric, a fine fabric which seems to indicate that the raw material was actually screened before the manufacturing, before the mixing of the element happened. Simply put, the big inclusion were removed and the soil was possibly even sieved before the actual manufacturing. But we also could identify a coarse fabric that show fewer traces of pugging and kneading and present sort of a clear separation between fine and coarse fraction. Both feature, though, seems to indicate that this coarse fabric was linked to a hastier manufacturing event. So I think Maud would agree with me that possibly the most interesting, after we have talked for half an hour, the most interesting aspect of our presentation, the best is for last, are actually the seagrasses that were added to the mix. Seagrasses have been identified in the bricks, in Minoan bricks, in several sites in Malia. And not only Malia, sorry, in Minoan Crete. They belong to different family of Marine-weeds, Posidonaceae, and also Zosteraceae. I have to say that in Malia, only Posidonia oceanica has been identified, and the numerous salt efflorescences recorded in the geoarchaeological sample that I usually show on top of the seagrasses impression indicates that these plants were not washed in fresh water before they were incorporated in the matrix, in the mixing. And this is actually also confirmed by the numerous small marine gastropods that were found within the bricks. In this case, I wanted to show you a seagrass that I collected a couple of years ago and with all the small gastropods still attached. So this is how the seagrasses were collected from the shore and then added to the soil mix and to water to create the mixture to produce the mud bricks. So one of the key questions that we were trying to understand is why people start using seagrasses. What is the reason behind it? Is it just opportunistic? Are they easily available? Or there is some other reason that it's worth investigating? So next. So I ran some experimental archaeology on both creating briquettes, actually with both chaff, barley, and seagrasses. And here you can see the morphological difference. So I thought this was quite nice because it's a bit self-explanatory, the difference of void between the chaff, the one that you have on the left, and the seagrasses. The seagrasses are not completely burned because the temperature we reached with this specific experiment that I conducted when I was a fellow at the Wiener Lab was not high enough for the seagrasses to burn, just to burn the chaff. So why were people actually using the seagrasses? So we came up with several reasons. First of all, I could imagine that to most of you, it might seem surprising that Minoan use a vegetal temper that brought salt into the mud bricks, but the presence of salt prevents weeds from actually growing and in generally even grass from actually growing, sprouting from the mud brick. And in ethnological circle, adding a pinch of salt to the mud bricks mix is actually quite a common phenomenon. The second point is that Posidonia oceanica is a natural fungicide which prevent harmful fungi to grow within earthen construction. And this is one of the reasons it's still used in quite a few countries as a natural vegetal temper. The other reason is that the seagrasses released the water content in the mud brick slowly, thus preventing them from shrinking too abruptly while drying and guaranteeing their fibrous nature. It's actually guaranteeing also longer lifespan to the bricks. We noticed that the bricks that were characterized with seagrasses were actually well preserved in comparison to the bricks that just presented chaff as vegetal temper. So one of the last experiments that I actually ran was to try to determine if there is any thermal the thermal properties of both the chaff and seagrasses. And as you can see from this graph, there is a slightly difference even in thermal behavior between the two briquettes. That seems to indicate that bricks that have a higher percentage of seagrasses have a better thermal performance than bricks with just chaff. Next. So, bringing our talk towards its natural conclusion, we noticed that the geoarchaeological data that we have collected enable us to answer the three research questions that we came up originally. So we were able to determine if there was continuity of raw source material. We were able to determine specific changes in the manufacturing process and construction process. Next. To sum it up, back to the comic strips that is giving you the breakdown of the different phases, we were able, for the first phase, we were able to determine that raw materials can be linked to deposits within a 2-kilometer radius from the core center of the site, which meant that even the manufacturing of the brick could occur nearby the original deposit. Second, when we were thinking about the mixing of the different elements, we could provide evidence that the seagrasses were procured locally from the protopalatial period onwards by just naturally collecting the one deposited in the shores around Malia. I want to point out that you do not, and I think it's quite an important point to highlight the exceptionality of Minoan bricks. We do not have the use of seagrasses in the period before the protopalatial period, and we do not have after the neopalatial period in Crete. Once the raw materials have been procured and some of them processed, as we have seen for the seagrasses, they were mixed together with water and blended for a couple of days, up to a week, depending on how long it will take for lactic acid actually to form and enhance the matrix cohesion of the mixture. We see traces of this final phase of kneading and pugging, especially when the mudbrick maker were preparing the mixing before the actual molding in the microfabrics of the bricks. The molded bricks were then left to dry for a few days, depending clearly on the climate conditions, but the deformation of some of the bricks that models show at the beginning of this seminar indicated that most of Minoan bricks were not dried completely before they were incorporated in the palace walls. But this may also indicate that the core of the bricks, due to the water retained by the seagrasses, could have been moist, even though the external part of the brick gave the appearance of being completely dry. Just to give you an idea, I ran some experiment, and the seagrasses retain water up to 3 years after they've been collected from the shores. And now I'll pass back the baton to Maud to finish the presentation.
Yes, so I'm speaking again. You can hear me? Okay, so as we pointed out earlier, many mudbrick walls in the palace in the Neopalatial Palace at Malia, which is the period for which we have the best evidence, are part of coherent structural and configurational architectural units. So one may expect, seeing the coherence of the Malia Palace master plan, to see some sort of homogeneity in the mudbrick walls of these different clusters. But this is, and strikingly, not the case. There is, in fact, a marked heterogeneity in mudbrick construction in the Neopalatial Palace, which is highlighted by the diversity of mudbrick masonries, and which suggests that each mudbrick architectural unit was erected by a different team of builders. This heterogeneity is also reflected by the dimensions of the mudbricks. There is only a maximum of 2 mudbrick sizes within each architectural unit, while the differences in dimensions between the separate architectural units are pronounced. This indicates the use of distinct molds in the different areas of the Neopalatial Palace and suggests that mudbricks were not mass-produced to be used indifferently throughout the edifice when it was rebuilt at the beginning of the Late Bronze Age, but they were produced separately by each building team, who then used them to erect its own mudbrick architectural unit. This indication for the segmentation of the building project, segmentation means its completion in separate building events that involved separate building groups, is further enhanced by the diversity in mudbrick fabrics. As we said earlier while describing the macroscopic composition of the mudbricks, there are strong dissimilarities between mudbricks with a homogeneous or fine macrofabric and those with a significantly coarser and heterogeneous macrofabric. And this macroscopic diversity is confirmed by the variations in the mudbrick's microscopic composition as seen through geoarchaeological analyses. This indeed corroborates the clustering based on macroscopic observations by showing geochemical and petrographic coherence within architectural units and small variations between separate groups of walls. So as far as geoarchaeological analyses are concerned, there is limited variability in raw materials. This is this local resource exploitation Marta has been insisting upon, but there are differences between walls clusters that are significant enough for corroborating the segmentation of the Neopalatial building project, highlighted by the macroscopic study of the mudbricks. In addition to highlighting the participation to the Neopalatial building project of various teams of builders, our study shows how the skills of the builders varied. Extensive use of mudbrick architecture on the site of Malia from the pre-palatial period onwards must have contributed to the development amongst its inhabitants of the practical knowledge necessary to produce structurally efficient mudbrick walls. Variations in mudbrick masonry, composition, and performance throughout the edifice indicate that while some architectural units seem to have been erected by true master builders, marked here in pink, others attest the work of less skilled builders, marked here in red. So this is a surprising observation for a palace for which one would expect the participation to the construction of skilled builders only. It is also in stark contrast with the construction in the same Neopalatial building project of elaborate cut stone walls, which we have argued in other publications, were not built by locals, but by specialized masons who had traveled from Knossos. The diversity in the origin, skills, and most likely status of the builders who participated to the construction of the palace at Malia at the beginning of the Late Bronze Age is thus demonstrated not only by our study of mudbrick remains in the palace, but also their assessment against other building techniques in the edifice. So we'll take some questions, I guess. Thank you very much for your attention.
Thank you.